What's up everyone? I am back with another video. Hope everyone is doing well. It's very rainy, actually unseasonably cold right now here in Philly. I think we're getting some remnants of tropical storm Debbie coming up along the eastern seaboard. So we're getting a lot of rain, almost dangerous amounts, so got some flooding and whatnot. But anyway, we're not here to talk about weather. We are here to talk about electronics and this little circuit board. Anybody want to take a guess as to what this is from? Anyway, so we're going to talk about a piece of lab equipment. This is a work-related video that I am working on. So the month of August for most people might be a time to go to the beach, go on vacation, but for me it is time to PM or perform calibration verifications on our thermal cyclers, or they're also known as PCR machines. And I actually am in the process of recording a video for another PCR machine, a different make and model. So I won't go into too much. I kind of cover what they're about in that video. But anyway, I guess I can do it here too. PCR stands for polymerase chain reaction, and so these machines are used to amplify strands of DNA, make more copies of DNA. All right, and so they do that by bringing up the reaction temperature of the DNA, cycling it from high to low and back up again, and that's what we use them for. And so anyway, let's get into what's going on with this machine. I'll it's out in the lab right now. We have about a half a dozen of them, maybe more of this model thermal cycler. It's a SimpliAmp. So they're very common. They're a workhorse. They usually work pretty well. But there's one thing I've noticed in these that I'm sure is pretty common. Anyway, so this is a portion of a PM report that I do, and you can see here we've got some fails. Alright, so this is temperature verification. So this is just checking the accuracy of the set temperature, and you can see here the spec is plus or minus 0.5. Actually, for this particular instrument, it's actually tighter. It's really plus or minus 0.25, but we've developed these in-house standards based on our application needs. Plus or minus 0.5 is fine, and temperature uniformity is actually more important to us, But anyway, these are falling out of spec even for this wider accuracy spec, as you can see. All right, this is pretty common on these instruments. I've seen it on a lot of them. Over time they just start to get more inaccurate, and only I never see it in where they're just too low in temperature. It's always they're just too high. And I've always thought it's probably due to the fact that they're not dissipating heat properly, so they do use Peltier elements that are on a big heat sink, and maybe that they're attached via some thermally conductive paste or adhesive, and maybe that is starting to break down due to constantly cycling of the temperature, and they're not able to dissipate heat as well. And that's kind of what I always thought was going on. It could be that the Peltier elements themselves are just starting to break down, but I was always curious if there was a way to resolve this without replacing parts. Most equipment like this that does any type of temperature control will have a way to calibrate it, to set an offset value. That's common with PID controllers. So unfortunately, this doesn't have anything like that. You're not going to find any trim pots, and I forgot to kind of go into what this is. This is the thermoelectric module for the SimpliAmp thermal cycler. There's actually 3 of these because you have 3 zones on the block, and I've got one here. This is an example from a SimpliAmp, and I apologize if I'm kind of jumping around all over the place. I'm not doing this scripted. I never do, so I'm sorry if I'm kind of scatterbrained right now, but this is at the block. So you've got these reaction wells, and when you together you've got 96 of them, because PCR plates usually come in as a 96 or a 384 well consumable, and you would stick your reaction, you would aliquot it into one of these wells, and you'll get a better idea of what it looks like when we look at the actual unit when it's together. But these are adhered to the Peltier element underneath it. And you can see that's where the RTD, it's a PT1000, is attached. And so these are usually on top, and that is the Peltier element right there. And actually, here's one that kind of got shattered. They're pretty delicate, but you can actually see the semiconductors that make up the Peltier element right there. So Peltier elements are made up of semiconductors. You've got these P and N junctions that are made up of, I believe, bismuth telluride. That semiconductor just does really well with a wide temperature range. And what you'll do is depending on what the polarity is across this Peltier element, it will heat for one polarity and it will cool for another. And so that's pretty much how these work. And of course, you've got a temperature sensor to monitor the temperature. And generally with these PCR machines, you will have a number of Peltier elements. Sometimes in this case you've got 3. I've seen other units that have 6. For example, the other video I'm working on, that one, there's 6. And there's a number of reasons for doing that. You've got better control, but also it allows you to put a gradient across the block, which can be helpful for certain applications. But anyway, that's what they look like. And of course you got this big heatsink. So when you've got to go from a hot temperature to cool, you got to remove that heat somehow, and that's what this big heatsink is for. There will be a fan underneath it that will pull that hot air away from the heatsink to allow these things to cool or maintain a certain temperature. That is how they work. All right, and so back to this guy. This is the thermoelectric module that will control one of those Peltier elements. And so this is where the let's see, oh, got it upside down. This is where the RTD will connect. This is where the Peltier element will connect. And like I said, you've got to do 2 things really with what this controller does. It will control the polarity of the voltage across the Peltier element, and will control the amount of current being delivered to it. You know, so you got to be able to do that with these. And manufacturers will, there are a few different ways you can do this. So basically on this guy, for example, usually for the polarity, you've got a half bridge or full bridge, I'm sorry, H bridge that will, configuration that will do the switching of the polarity. I do see 2 MOSFETs right here. These they might be dual MOSFETs, I'm not too sure. I haven't really looked at the what type they are. So that might be your H bridge right there. And I do know on this L5105 SD is a H bridge driver, or might be a half bridge driver. So yeah, I forget, but so that might be for the polarity. And then of course you need a way to control the current, which I am not quite sure how they are doing that. I do see a switcher up here, this LM2676. So that might just take that. This is supplied 24 volts, so that might take that and step it down. I've seen some use a current mode PWM to control the current, but you know, I haven't really looked into that too much on this board. But and then of course you've got this microcontroller that is, you know, controlling the whole show there, so to speak. I do see a couple logic devices on here as well, but yeah. All right. So what I'm going to show you guys though is a mod that I came up with, a very simple mod that you can do on this board to bring the temperature back into spec. Okay, and right now I'm actually testing it out. I'm running a temperature verification test on this one that failed, and I'm going to show you the results. We'll compare it with the results I just showed you, and then I'll show you what the mod is. It's really simple, and why I think this will be really helpful to other owners of this equipment is because you don't need a whole bunch of skill to fix these. It's going to be helpful to know how to solder, but even a person with low experience with a soldering iron could likely do this watching a couple of videos on YouTube. It really doesn't take that much skill. So, and it'll save you a ton of money, because the problem with these is Thermo will not sell you replacement parts for these. It's very interesting what pieces of equipment they will sell you parts for and which ones they won't. So for larger equipment that's not as complex, like incubators, centrifuges, freezers, you can get almost any part within that instrument to fix it. But for the more complex, more expensive stuff, definitely the analytical type equipment, they will not sell you parts. And I believe this guy falls in this category. It's not really an analytical piece of equipment, you know, it's just a thermal cycler, but still. So you're kind of out of luck if this happens to you. I mean, yeah, you can ask Thermo to fix it, but it's going to be thousands of dollars. So this mod won't even cost you $1 if you have the tools to do it, like a soldering iron. You know, it just requires a resistor. And so again, once this thing is finished, we'll go out and take a look at the results, and I'll show you how you can do this and how it works. Well, check that out. This is after doing this modification that I'm about to show you guys. Every single zone passed. Zone 2 just barely made it. And yeah, I guess zone 3, but again, this is the spec for this instrument. Our spec is a tiny bit wider in-house at 0.5 plus or minus 0.5 degrees Celsius, so even if they did fail, it still would have been okay for our internal specifications. So, but this is fantastic. Yeah, so the way that I perform these tests is using this temperature verification kit. So this is a kit that you can get from ThermoFisher. They don't manufacture it, as you can see, but it is a digital thermometer with a 9-channel probe. Alright, that way you get a good reading of the block. And then of course you have a probe on the top so that it can measure the heated cover. Alright, well, we're done with that for now. But yeah, so this is very expensive through Thermo, probably cost you close to $10K. You can get them from other places for much cheaper. You can find them, probably look on eBay, find them used for a lot cheaper. And you do need to get them certified every year. One thing I will say about that is only go to the manufacturer to get it certified. Now, Alpha Technics is no longer, they've been dissolved or bought by TE Connectivity. So that's who you would reach out to if you own one of these and you want to get it calibrated, or if you're looking for one and you need it calibrated, because I use another third-party calibration service for some of my other calibration standards, like tachometers, other digital thermometers, and they do great work. They advertise that they can calibrate this, And that depends on what your definition of calibration is. If you're just verifying it with another standard, yeah, they can do that. But if it's out of tolerance, they can't make the adjustment. They don't know how, they don't have the procedure, which is why if you're advertising as a calibration service company, I would assume that you can do the calibration adjustment for whatever you're advertising. Or you should at least state that. It shouldn't be on you, and that's kind of what they told me. So anyway, I would not use anyone for these but the manufacturer, only for that reason, just to save you some money. But anyway, that's what you need to do these calibrations, and I can kind of show you where you can access that. So if you go back to maintenance and services, on the interface you go to block verification test, verify block temperature, there's the heated cover test, temperature verification, and then next I'll do temperature non-uniformity, not in this video. That should pass fine though. And you need to hook this guy up to the RS-232 port in the back. But yeah, so that's just a brief rundown on how to do a calibration verification on these. But now that we've got the data, let's take a look at one of these TE modules again with the mod. And I can kind of walk you through how it works, and we'll wrap up. Alright, so let's take a look at this temperature module. So this is the mod. That's it. Like I said, just one resistor. This is a 4.7 mega ohm resistor, and it's tied to the RTD, one of the pins to the RTD sensor. This other pin is tied to ground, and then it connects to R38. That's it. Now, why are we doing that? So, I traced out the schematic. Of course, as in most cases, the manufacturers of this kind of equipment, they're not giving you schematics. So, I traced it out a little bit. And so, this is the RTD. Alright? It's a PT1000, like I said. And it then connects to R38, which is a 5K resistor right there. And, well, you've got it connecting to this op amp, U11, and then this series of resistors connects to the inverting input, or inverting input, I'm sorry. And then from here it connects to this ADC. So that is how it's which probably then connects onto the microcontroller. That is how the microcontroller knows the temperature of the block. It's taking that analog signal, converting it to digital, which then goes to the microcontroller. This R38 is basically a shift or offset shift resistor. And so by decreasing this resistor, that's going to be read as an increase in temperature. If I were to increase the resistor, it would be a decrease in temperature. And that's exactly what we're doing. We're trying, the temperature is being read too high. We want to offset it so that it's reading where it should be. And in order to do that, we had to lower this 5K resistor. And without removing it and replacing it with an entirely new resistor, you can just put one in parallel. And that's exactly what we're doing. We're putting a 4.7 mega ohm resistor in parallel with this R38. Alright? Now, why 4.7 mega ohms? That's very high, because we're trying to change this value only by a tiny bit. If you were to look at an RTD temperature chart, for example, you would probably find that, let's pull one up and I can kind of show you what I mean. Okay, so this is a temperature, comparing temperature and resistance for a PT1000 RTD, which is the exact same probe that these SimpliAmp PCR machines use. And this is what I'm talking about. Look, so a jump from 0 to 10 degrees Celsius, that's a 10-degree jump, is the RTD is going to respond to that by increasing resistance by 40 ohms. All right, so we want to bring that temperature down by 0.5 degrees Celsius, basically. So if a 40 ohm increase is 10 degrees Celsius, you know, you can imagine how little 0.5 degrees Celsius would be. And so that's why you need such a large, if you're putting this resistor in parallel with it to bring the total resistance down, you need a much larger resistor to do that, to only make a small change. And that's basically what we're doing. Basically trying to drop that resistor by a very little bit. So that just gives you an idea. Now, it took me I had to do some playing around. I didn't pick this right off the bat. I played around with some resistance values and tried a few different ones, and then kind of narrowed it down to this value here. So that's what I did, and I think this would work great for any of these instruments. Now, you may not. It depends on how much your offset is, one, and also, you know, every instrument has some little differences. So 4.7 mega ohms may not be what you require. So I would start with that, and then what I would do is grab, if you're trying to do this modification, if you've got a similar situation, I would grab something like this, and you're not too familiar with electronics, or you have a basic, a little bit of experience. Grab something like this. You can get one of these on Amazon. They're not quality resistors, but you get a whole ton of values, and then you have a few to play with to make adjustments. And then once you find one that works or gets you close, then you could go to a distributor like Mouser or DigiKey and find some nice quality resistors that are gonna get you right in the ballpark of where you need to be. That's what I would do. Now, the problem with this mod is it could definitely be optimized, that's for sure. But one of the problems is, if doing this exact mod, putting a resistor in parallel with R38, that's only going to allow you to get decreases in temperature. So, if your case is the temperature is too low, which I have never seen before, in these instruments I've only seen it get too high. Unless there's something really wrong, and that's an entirely different situation. But in most cases, it's going to be that the temperature is too high, and this will work just fine for this type of modification. But it would be nice if I could figure out a way to add a trim pot in here. I was thinking of maybe, instead of putting a resistor here, put like a maybe lower this or increase this resistor value to something a little bit higher, like say 5.1, and then that way I can put in like a 500K pot and have some play, like a 10-turn pot. Or I need to figure out this circuit a little bit better and find a better spot to put a trim pot so that I have a little bit more ability to make adjustments. It'll make adjustments a lot easier. Now, I'd be curious to know how Thermo is making calibration adjustments on these if they can, via software that hooks up to the instrument. I have no idea, but they certainly aren't sharing that with the customer, that's for sure. So, yeah. But this will definitely work. And if you get a good quality resistor, a precision resistor that is very accurate, it'll likely last for a pretty long time. And then, if it falls out of spec again in another 5 years, you know what to do to fix it. So this will definitely improve the longevity of your equipment for an affordable, amount of money. But yeah, that's pretty much how this works. I hope you guys found this interesting. I'm gonna do this for the other one as well, and yeah, if you guys have any comments, please, or feedback, leave it in the comments is what I mean. And if you have an idea of how I could make this mod better, I would love to hear your thoughts. But thank you guys for watching, and I'll catch you at the next repair. Alright.